This is a companion video to the video on 3.5, which is on operations of functions, and we're going to primarily talk about composition of functions. And it might not seem like it at first, and we're going to talk about all kinds of strange things, but at the end of the day, all this really is composition of functions. The topic, though, of the video is called difference quotient. To get started, I want to ask you, like, if I were to ask you what's happening on this graph, like what would you say? And I think your answer will probably depend on like what class you've taken. So if you've taken physics, I think it's probably like muscle memory, like brain muscle memory at this point. You know exactly what this is. But if not, that's fine. We can just think about it logically. So along the horizontal axis we have time, and along the vertical axis we have distance. So think about what's happening. We have something that at time equals 0, its distance is changing. So it's increasing, right? As we move to like say these are in seconds or something, it's gone some amount of distance. And after another second, it's gone another amount of distance. And so if this was a straight line, you can imagine we have something that is traveling at a constant rate of speed. So if it goes like 5 miles per second, that's pretty fast. Let's say 5 feet per second, right? Then every second we would go an additional 5 feet and we'd have a straight line. So if you've taken physics, you know that a straight line on this graph represents something that is traveling at a constant velocity. And you also know that a curved line on this graph represents something that is not traveling at a constant velocity. And if it doesn't travel at a constant velocity, that means that velocity is changing, which indicates either acceleration or deceleration. And for this particular graph, because my curve has this, we call this like a concavity, in the way shown here, that we have like a slope of the line right here that's kind of, it's one thing, right? But then the slope of the line over here is less. This indicates to us that we have a deceleration. In fact, the slope of the line here is representative of the velocity. So let's expand on that thought a little bit, okay? So what might this be if it's a decelerating? Maybe it's a car that's slowing down to come to a stop. When we have horizontal line here, think about what that is. Time is passing, but no distance is changing. That means something has stopped, right? So it's a car, it was going, and then it's slowing down because there's a red light or stop sign or something like that. Let's expand on the idea here of slope a little bit more. If I, now let's get rid of the context of time and distance and just say it's x and f of x, right? Well, x's and y's. If I asked you, what is the slope of the line between in this region right here? So I'd be saying like, what's the slope of this line? How would you even approach that? Would you say that I'm taking like this point right here and this point right here, and I want to know that slope? How can I find the slope of a curved line? I mean, the answer is that you can't, right? It's curved. It doesn't have slope. Only lines have sloped. Only like straight lines have slopes. So what you would have to do then is take kind of a line that looks like this, right? And maybe find the slope of that line. Well, what's that called? We're going to zoom in. So this is the same little section of the graph here. We have these 2 points now, and if we were to draw a line between those 2 points, that line is called a secant line. It's a line that touches a curve twice, okay? And you can see that we're going to basically do, we can write a little, we can put a right triangle on here and see that, you know, we know how to calculate slope here, right? It's a change in y values with a change in x values. So our x values are x1 and x2, and our y values are y1 and y2. But again, because we're talking about y as a function of x, we can, instead of saying y1 and y2, we can say that they're f of x1 and f of x2. Okay, so the slope of the line is a change in y over the change in x. Or if we use this function notation instead, we get this equation for the slope of this line. And this is called an average rate of change. This should all kind of make sense to you. This is, if you're asked to find the average rate of change of a curve like this, you take the starting point and the ending point. Those are your 2 points, and you do the slope formula, and that's it. Now, what if instead I asked this question, right? What's the slope of that line, like that little section of the line right there? Now, this is where this gets a little interesting. So we have I couldn't draw the box infinitesimally small because you wouldn't see it, but we're assuming that we have infinitesimally small differences in x values here. So we're saying that the distance between these two x values of these 2 points is infinitesimally small, and we're going to call that distance h. Okay, so if that's the case, then you can see that the coordinates of my x values for these two, between these two different points, is going to be different by h. We're just going to add h, right? And the difference in the y values, like if I'm plugging in x to get f of x, and I'm going to plug in x plus h to get f of x plus h with the y value here. Now, think about this, okay? If I zoomed in so infinitesimally small that instead of it being a secant line that I'm drawing between 2 points, the distance between those 2 points is so small that I'm effectively drawing a tangent line. Okay, and if it was distance versus time, I would be drawing a line tangent to the distance versus time graph, but I'm just drawing a line tangent to this graph, period. And what that's called is called an instantaneous rate of change. If it was distance versus time, I'd be talking about an instantaneous velocity. Okay, and the equation then that we would use based on the exact same slope equation would be this. Now these terms, right, this is y2 essentially, and this is y1, and this is x2, and this is x1. And we're doing this for values of h that are approaching 0. They're basically 0, right? We're assuming, I mean, this is infinitesimally small. So what's infinitesimally small? 1 divided by infinity is essentially what that's talking about, which is effectively 0, but it's not 0. It's like almost 0. It's like so close to 0, like 0.0000000 forever 1. Okay. This is what's called the difference quotient. And it comes from the formula for slope. And we just write it like this: f of x plus h minus f of x all over h. Now, what's happened to our previous, compared to our previous formula we showed, remember that the denominator here was x plus h minus x. The difference in the x coordinates, this is just h, right? So we just simplify it by writing h there. So this concept here, now notice, look at what it looks like. I said this is about composition of functions. That's what it is, right? We're plugging in x plus h into a function, right? We're basically evaluating. I guess it's not even composition of functions. It's just evaluating a function, but doing it in a kind of a weird, specific way. There is some math and some subtraction of functions, some operations of functions, things that we need to do here. But it's not particularly difficult. It's conceptually, this is an important thing. Let's elaborate on that just a little bit. So this is from the previous slide, right? I have this infinitesimally small value of h. Now, how do we say that like efficiently in math? We use something called limits. Okay, we talk about limit notation. We say, what this here, I'm going to say what this says. This is the limit as h approaches values of 0 of this function here. Or you say the limit of this function for values of h that approach 0. There's two different ways kind of to say that. The function being f of x plus h minus f of x all over h. And you can expand this idea of limits to a lot of different things, but the main idea is we're kind of examining what's happening to a function at specific points, right? If we want to know, what's happening at the end of a graph, like what do we do then? What if we want to know exactly what's happening at a specific point? We use limits for that. Let me show you what I mean by that here in a second. So here's a graph, right? Let's say I was particularly interested. It looks like something weird is happening right here. It looks like there's an x value of -1, right? So what I might do, if let's say that this purple line is, should have drawn it that way. This purple line is f of x, right? If I wanted to know exactly what's happening to this function at this line, at this point, this x value of -1, I might say something like, okay, what's the limit of f of x as I approach a value of 3 from like the right side? Or what's happening to this function maybe as I approach a value of 3 from the left side? That would tell me some interesting information about this graph, because I would be able to do this kind of limit operation at a specific point and say, oh, it looks like it's going up forever there, right? And then we're going to eventually work on how to describe what that is what does that mean going out forever? And then maybe I'm also interested in what's happening like way out there forever, all the way to the right. Well, then maybe I'd say what's happening, what is the limit of f of x as x is approaching values that are like infinity? Like, so what if I put in infinity, like what's happening to the y values, right? It's a way we can examine behavior of a graph. Now in precalculus, we'll use this when we talk about polynomials and rational functions, but it is absolutely the case that there are certain points of a graph we're super duper interested in, and you'll learn about those in calculus. So you're going to see this notation, limit notation, as x is approaching some value or whatever. You're going to see this often, and so it's something to get used to now because you'll see it a lot more in calculus. So let's actually use the difference quotient now. Let's do the arithmetic involved. So again, this is the difference quotient. We're calling it the limit as h approaches 0 of this function f of x plus h minus f of x is divided by h. Here's the steps. Okay, we're just going to write what f of x is. We're going to then plug in x plus h into f of x and write what that is. We're going to subtract them. We're going to and simplify. We're going to divide by h, and then you should see the situation where everything in the numerator that doesn't have h in it will cancel out with other stuff in the numerator. And then you're going to divide by h and factor, and the h's stuff is going to, some of the h stuff is going to cancel out, and then you're done. And it's going to give you this thing, and that thing is called the difference quotient. So let's, and it's actually called one other thing that is very important. It's a huge foundation of calculus, but I'll let your calculus teacher tell you what that is. So let's do 3 examples. The first one is this. I want to know what is the limit as h approaches 0 of this function. Okay, so I already got the first step, which is what f of x is. Now I want to know what is f of x plus h. Well, I'm going to just plug in x plus h. So it's x plus h, quantity squared, minus 3, which is going to be, after you multiply x plus h out, x squared plus 2xh plus h squared minus 3. Did it. Okay, now we're going to do the subtraction in the numerator. So I want to do f of x plus h minus f of x. That's going to be this, x squared plus 2xh plus h squared minus 3, and now we're going to have like it's a minus this stuff, right, because minus f of x, so it's going to be negative x squared plus 3, so minus x squared plus 3. Right, now let's like simplify this subtraction, right? This x squared and this x squared cancel because it's positive x squared and negative x squared. This negative 3 and this positive 3 canceled. Okay, so what we're left with then after doing the subtraction is that it's 2xh plus h squared. That's simple enough. And then we're just going to divide by h. So we're going to actually do this part now. F of x plus h minus f of x. We're going to divide that by h. So we got 2xh plus h squared divided by h. And then we can factor an h out on top. And then we can cancel these h's. And what we're left with is the difference quotient of 2x plus h. And that's it. Right? Well, what is h? Well, remember what h is, right? H is, we're interested in what h is as h approaches, or what this is equal to as h approaches 0. So we're going to kind of eventually, we're not going to make this leap yet, but we're going to say, right, pretend h is 0. Well, then the difference quotient is 2x. But not really. Like, there's some more vocabulary and like knowledge you need. So I'm not going to just say that. For now, your answer is 2x plus h. That's it. Let's do another one a little bit more difficult. Okay, here we have f of x already, 3x squared minus 2x plus h. So we're going to say, all right, cool, what is f of x plus h? We're going to plug in x plus h. 3 times x plus h, quantity squared, minus 2 times x plus h plus 1. So this is going to be 3 times x squared plus 2xh plus h squared minus 2x minus 2h plus 1. 6x squared, oh, sorry, 3x squared, I can do math. 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 1. Cool. What does anything does anything cancel out here? Oh wait, forgot to. Oh, that's f of x plus h. Okay, now we're gonna subtract f of x, right? So f of x plus h minus f of x is equal to all that stuff. We just wrote 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 1. Now subtracting f of x means we're going to make it negative 3x squared plus 2x minus 1, right? It's all this stuff, f of x, subtracting it. So distribute a negative 1 through. All right, what cancels out? Let's see, positive 2x and negative 2x. Positive, negative 3x squared, positive 3x squared, and the positive 1 and the negative 1. So what we're left with after we do that is this. We have 6xh plus 3h squared minus 2h. So now we're just going to divide. So f of x plus h minus f of x divided by h is going to be this, 6xh plus 3h squared minus 2h all divided by h. We can factor the h out on top, and we'll have 6x plus 3h minus 2 divided by h. The h's will cancel out, and we're left with an answer of 6x plus 3h minus 2. Now, usually you put the h thing last, so you might want to write this as 6x minus 2 plus 3h, but that's kind of up to you. Both answers are obviously correct. Also, just a side note here, I think H is the strangest letter. How do you spell that? Was it like H? But then it has H in it. It's just a very strange sounding word. Whenever I teach this lesson, I just like, oh gosh, H. I say it so much. It's just so strange. Okay, anyway, that's just me being weird. But let's do one more. Next one will be kind of strange. Okay, f of x is equal to 1 divided by x minus 1. We want the difference quotient here. So we already got f of x plus h is equal to 1 divided by x plus h minus 1. Now we want to subtract these. So this sucks. Okay, so f of x minus h minus f of x for this is 1 divided by x plus h minus 1 minus 1 divided by x minus 1. We only can do this by getting a common denominator, right? So let me rewrite that with a little bit more space. We're going to have to multiply this by x minus 1 over x minus 1. And we're going to have to multiply this by x plus h minus 1 over x plus h minus 1. So when we do this math out, we will have x minus 1 minus x minus h plus 1 in the numerator divided by x minus 1 times x plus h minus 1. Okay. We can simplify some stuff because we have x and negative x, and we have 1 and negative 1. So really what we have here is just negative h divided by x minus 1 times x plus h minus 1. And then we're just going to divide. So f of x minus h minus f plus h, f minus f of x divided by h is equal to negative h divided by x minus 1 times x plus h minus 1, and we're going to divide this by h. I'm just going to write it like this because it's confused. It always confuses me to have multiple division signs in a big fraction. I hate complex fractions, so I'm just going to do multiply by the reciprocal, which is also known as the Missy-Elliott method of complex fractions, by the way. Put your thing down, flip it, and reverse it. So now we're just going to cancel out these h's, and what we'll be left with is this. We'll have negative 1 divided by x minus 1 times x plus h minus 1, which is disgusting but correct. So that's the difference quotient there. Anyway, there's nothing terribly complicated about this, but I cannot overemphasize how important conceptually what we've just done here is. When it comes, what is the difference quotient representing? It's representing, like, this graph this is a graph. Like, we can graph this. It would look something disgusting. Something gross. Maybe like, I actually don't know off the top of my head. I believe it would be. I believe it will do something like this. And what we've just done is come up with this kind of formula right here, where if I plug in a value for x, it'll tell me what the slope of the line is at that point. So if I were to like plug in a value for x right here, the slope of the line that's tangent to that point, so like kind of like that, whatever I plug in for x, it'll give me that value, which is kind of crazy. I mean, it's not kind of crazy; it's insane, actually. So anyway, that is how you do the difference quotient, and The purpose of it is very important, and you'll learn that. You'll definitely learn that and be clear why that is when you take calculus.